So we're essentially seeing what would be the rate of heat flow. So we have a thickness. This is for part A. We have a thickness of 3.5 centimeters, and this is going to be 0.035 meters. We also have a surface area of 0.95 meters cubed. The temperature of the clothing is going to be equal to negative 18 degrees Celsius, so the outside temperature. And then temperature of the skin, S, is going to be 34 degrees Celsius. And the thermal conductivity of goose-down is going to be equal to 0.025 joules per second per meters per degree Celsius. And this number is actually, it makes sense in the sense that the lower the thermal conductivity, the less efficient a material's ability to disperse heat throughout its own dimensions. So essentially, if you have a very low thermal conductivity, you have a very low thermal conductivity with an assumed very sufficient thickness, we can have a very high temperature, a very low temperature on either side of the jacket, and essentially the other side of the jacket will not have the same temperature. There'll be a very large temperature gradient because, again, the thermal conductivity is just so low. Thermal energy is not dispersed efficiently throughout the material, which is good because you don't want it to be you don't want to lose heat from your body to the outside. So for part A, rate of heat flow, we can say Q over T. That's going to be the rate of the heat flow is going to be equal to the thermal conductivity of goose-down times the surface area, T sub S minus T sub C, all divided by L. So this is going to equal the thermal conductivity of 0.025, the surface area of 0.95, and then we have 34 minus negative 18, all divided by the thickness of the jacket, so 0.035. And we get that this is going to be equal to 35 watts. Now, this is extremely low. This is extremely low, which is good because if this is extremely low, that means that the rate of heat flow is going to be low, and that means that one is going to retain their own warmth if they're wearing this jacket. Now, for part B, it's a little bit different because now the jacket is wet. So now we're going to use the thermal conductivity of water, which is 0.56. You can see that this is much, much bigger than the thermal conductivity of goose-down, which we're going to assume that will increase the rate of heat flow. We'll see. The length is going to be decreased now from 3.5 centimeters to 0.50 centimeters. So this will be 0.005 meters. So for part B, for the rate of heat flow, we'll have Q over T, and this is going to be the thermal conductivity of water times the surface area, T sub S minus T sub C, all divided by L. It's going to be the exact same numbers except for the thermal conductivity and the thickness. So we have 0.56, and then we'll have, again, times our 0.95, and then 34 minus negative 18, and all divided by 0.005. And we find that Q divided by T, the rate of heat flow, is going to be equal to 5,533 watts. Now, this is extremely high, which means that you are not going to last so long. The heat from your body is going to be quickly taken away and transferred to your immediate surroundings. Again, the thermal conductivity of water is so much higher than goose-down. It's much more efficient in dispersing its thermal energy, which means that your skin, essentially the water is going to be taking away, in a sense, thermal energy away from your skin. So that's why when you're cold when you're cold and wet, rather when you're wet in in very cold weather, no matter what you have on, you're gonna feel very cold. And that's the end of the solution. Thank you for watching.